All right, so this is my presentation on sea level rise effects on Philadelphia, Pennsylvania. This slide shows seasonal 3-month sea level estimates from two different sources, and it demonstrates the change in sea level in millimeters compared to the 1993 to 2008 average. As you can see, the graph is significantly increasing. This comes from two main contributors, the melting of ice sheets and glaciers, as well as the thermal expansion of the ocean itself. There is also a small amount of sea level rise due to a shift in liquid water from land to ocean, which is largely a result of groundwater pumping. However, this is much smaller than the other two contributors. And interestingly, the amount of sea level rise from each of these contributors was roughly equal from about the 1970s until the last decade or so. However, the amount of sea level rise due to melting, plus a bit from that liquid water land to ocean shift that I just mentioned, from 2005 to 2013 was almost double that from thermal expansion. And so all this is a result of climate change that's caused from the warming of the atmosphere by anthropogenic greenhouse gas emissions. Essentially, as we warm the atmosphere, we also warm the ice in the oceans that contains our planet's water. Because sea level rise is based on anthropogenic or human-based emissions, the amount of sea level rise that will occur in the future depends on how much of these pollutants we emit into the atmosphere. This graph shows various levels of sea level rise based on emissions pathways, which are essentially scenarios in which we emit small, intermediate, or large amounts of GHGs into the atmosphere, with GHGs being greenhouse gases. This presentation will focus on the high emission scenario in which we continue to emit significant amounts of GHGs into the atmosphere. This scenario also includes rapid ice sheet collapse, meaning that the large ice sheets such as those in Greenland and Antarctica do not melt in a steady and predictable way, but instead reach a tipping point after which they rapidly melt. And so based on SLR or sea level rise models of this pathway, the sea level of the contiguous U.S. could rise upwards of 7 feet by 2100, which is the number that will be used throughout the study. As you can see on the slide, there are various negative consequences from rising sea levels. Note that a wide variety of infrastructure can be affected by SLR, including roads, power plants, landfills, and more. And it can also lead to the permanent displacement of people living on the coast. So having gone through this brief background, this presentation is going to focus on the susceptibility of Philadelphia to the negative effects of sea level rise. I am a current resident living just outside of the city, and I was first introduced to this idea about a month after I moved here in the late summer of 2021. We experienced a significant rainstorm which led to extreme flooding both within the city and surrounding it. Although I grew up in a beach town and storm-based flooding really isn't anything new, this was different than anything I had seen before. And so this, coupled with my ongoing studies into climate change and its various effects, led me to want to learn more about how the city will be affected by the increasingly alarming issue of sea level rise. So this issue will be approached using the computational and visual benefits of GIS software. To begin, the 7-foot sea level rise scenario will be analyzed to visually understand the brevity of the inundation and if there are any trends to which areas are most affected. A DEM or digital elevation model will then be analyzed to understand which areas are closest to sea level and thus more likely to be affected by flooding. Finally, the land cover classification of the city will be computed and looked at in further detail to understand how the development of the city can influence coastal flooding. So first off, this is an overhead view of the city. It was produced by the U.S. Geological Survey, or USGS, Earth Resources Observation and Science, or AROS Center. The image itself was taken from the Landsat 8 satellite on September 27, 2021, which interestingly enough was the closest date I could find post that flooding event that I just mentioned. And it's displayed using the natural color band combination. It's the basis for much of the analysis that will be presented further in this presentation. So this map shows which areas in blue will be inundated under the 7-foot sea level rise scenario mentioned previously. The data was obtained from the National Oceanic and Atmospheric Administration Ocean Service Office for Coastal Management, or OCM. The values show, in this case, inundation based on 7-foot sea level rise above current mean higher high water, or MHHW, conditions. The data also is showing inundation at the highest high tides, and does not take into account things such as erosion, subsidence, or future construction. As you can see in the image, nearly the entirety of the coastline, shown on the right-hand side of this image, has some level of inundation. However, it is immediately clear that there are larger areas of inundation in the southern tip of the city, characterized by larger areas of blue in the map. In the next slide, this inundation will be analyzed to see if any areas of high population will be affected. A calculation was performed to determine the extent of inundation within the study area. And note that the data used to define the study area was obtained from the Carnegie Museum of Natural History from a data set on Pennsylvania counties. First, the area of SLR inundation was obtained using the Calculate Geometry feature in ArcGIS and was divided by similar data for the entire study area. And on the slide, both the inundation extent and the proportion of the city inundated are listed. So this slide shows the comparison of population versus the 7-foot sea level rise scenario as discussed on the previous slide. The population data was taken from a layer created by Esri titled USA Census Tract Areas from the ArcGIS portal. This layer includes the 2020 US Census Tract boundaries as well as the estimated 2020 total population from the Esri demographics team. Fortunately, what this comparison shows is that much of the inundation occurs in lesser populated areas, though there is still overlap with some higher populated areas. Especially looking at the southern tip of the city, much of these large areas of inundation occur in relatively lightly populated areas. But this doesn't mean that the flooding is occurring on just unused ground, as referring back to the Landsat image and also in the next slide as well, there's still plenty of roads, buildings, and other development here. And from personal experience driving near this area, there's lots of industrial activity, so inundation of this area could still have severe economic impacts. This is a very high-resolution image taken from Google Earth Pro of a portion of the southern tip of the city with the 7-foot SLR scenario overlaid. And as you can see, there's plenty of development that is still inundated. Next, I wanted to analyze the elevation distribution throughout the city to see if there are any trends relating to areas more or less susceptible to sea level rise inundation. Fairly intuitively, areas that are closer in elevation to the water level will be more likely to be inundated, as water has a tough time traveling uphill. Therefore, a digital elevation model was clipped to the study area to show the city's elevation. This DEM was obtained from the U.S. Geological Survey as part of the national map and has a 1/3 arcsecond or 10-meter resolution. Not surprisingly, much of the city, especially in the coastal areas to the right-hand side of the image, are at a significantly low elevation, meaning that it is likely easier for flooding waters to reach them. Note that areas in green and blue are the lowest in elevation, while yellow, brown, and white are higher elevation. And what this map tells me is that Philadelphia's low elevation makes it quite susceptible to sea level rise inundation. Finally, the land cover usage of Philadelphia was considered to understand just how much of the city was developed. Note that for this study, developed represents any sort of human development, including roads, buildings, sidewalks, etc. As well, essentially all of these developments are impervious, meaning that water cannot soak into them to drain. As shown on the slide, having an impervious surface instead of the natural vegetation that once existed in an area is poor for the natural hydrology of that area, and it can lead to increased stormwater runoff and frequent reduced groundwater recharge, which results in more frequent flooding, larger peak flood flow, and lower water table levels, among other things. Knowing this, it is extremely important to understand how much of the area is impervious, and thus more susceptible to these risks. Running a simple pixel sum of each class shown in this supervised classification map yields a development percentage of 71.9%, meaning that nearly 3/4 of the city is developed. As well, most of the vegetation is concentrated in large groups surrounding the various rivers in the study area, shown here in green. So the percentage of impervious surfaces in populated areas is likely higher. Also note that this classification was derived from the Landsat 8 image shown previously. So what this all means is that much of the city is at risk of more frequent and more severe flooding, as described earlier. The reason for this is that rainfall tends to be absorbed by soils in a process called infiltration in a natural waterway, before being stored as groundwater and slowly released into streams through seeps and springs. However, impervious surfaces restrict the amount of infiltration that can occur, which creates more stormwater runoff, and this can cause more water to arrive to a stream quicker, resulting in higher flood risks. This is just an interesting zoomed-in clip from the last map, which really shows how the flooded water follows the impervious surfaces of the roads around buildings. You can see kind of in the center, you can make out where roads are based on where the flooding occurs. So summarized in the slides are the findings from each of the maps shown throughout the study. In terms of the bigger picture, I think this research reaffirms what many already know and likely fear, which is that many coastal cities are at extreme risk of sea level rise inundation. An example that immediately comes to mind is New York City, which shares many geographical similarities to Philadelphia and likely is at a similar risk level. This is also a problem because, as Rebecca Lindsay writes for NOAAclimate.gov, in the US, nearly 30% of the population lives in a relatively high population density coastal area, and globally 8 out of the 10 largest cities are near a coast according to the UN Atlas of the Oceans. Therefore, understanding how a rising sea level interacts with an urban coastal environment is paramount to understanding how to mitigate the issue as best as possible. In the future, with more time and a larger budget, it would be interesting to delve into the environmental justice aspects of sea level rise to understand if any demographics or classes are disproportionately affected. It would also be interesting to perform a similar study on other larger cities, although many have likely already been done. Finally, I think the biggest takeaway from this research is that while we still have time before the sea level reaches a significant height as it did in this example, our actions now will have significant impacts on how severe the sea level rise will be in the future. Thus, it is imperative that we significantly reduce our GHG emissions in order to lessen the warming of our atmosphere and thus the rising of the sea level. And these are my references. Thank you so much for watching.